Welcome to Section 4, Lesson 1. Across the previous 3 sections, we worked with algebra entirely as symbol manipulation, combining like terms, evaluating expressions, solving equations and inequalities. Today, Section 4 opens with a different perspective, visualizing algebra as geometry on a 2-dimensional grid called the coordinate plane. The plane is the canvas on which every linear equation we solved in Section 3 will be drawn as a straight line, and the geometric properties of those lines connect directly to the algebraic properties of their equations. Mastering the coordinate plane is the gateway to all of analytic geometry, calculus, computer graphics, GPS navigation, and any field that mixes algebra with spatial reasoning. Today we lock in the plane structure, the ordered pair notation, and the quadrant sign convention, and over the next several lessons we will build up the full algebra geometry bridge. First idea on the board. The coordinate plane consists of 2 perpendicular number lines that cross at a single common point called the origin. The horizontal number line is called the x-axis, with positive values extending to the right of the origin and negative values to the left. The vertical number line is called the y-axis, with positive values extending up from the origin and negative values down. The 2 axes together create a flat 2-dimensional grid that covers the entire plane. The plane is also called the Cartesian plane, after the 17th century French mathematician René Descartes, who introduced this representation. Second idea, every point in the plane is named by an ordered pair of 2 numbers, written as the x-coordinate first and the y-coordinate second, separated by a comma, all enclosed in parentheses. The notation is x, y, like 3, 2 for the point 3 units to the right and 2 units up from the origin. The order matters. 3, 2 is a different point from 2, 3. The convention x first then y is universal across mathematics, science, and engineering, and reversing the order is one of the most common beginner mistakes worth being explicit about from the start. The 2 axes divide the plane into 4 regions called quadrants, numbered with Roman numerals 1 through 4 counterclockwise starting from the upper right. Quadrant 1 contains points where both x and y are positive. Quadrant 2 is upper left, where x is negative and y is positive. Quadrant 3 is lower left, where both x and y are negative. Quadrant 4 is lower right, where x is positive and y is negative. The quadrant numbering and sign convention is universal and worth memorizing once and for all, so you never have to rederive it during a problem. Today we plot 4 points, 1 per quadrant, in worked example 1, and identify the quadrant of given points in worked example 2. The coordinate plane consists of a horizontal x-axis and a vertical y-axis crossing at the origin. The x-axis carries positive values to the right and negative values to the left. The y-axis carries positive values upward and negative values downward. Every point in the plane is named by an ordered pair x, y, with the x-coordinate first. Here is the quadrant convention. Quadrant 1 is the upper right region where both coordinates are positive. Quadrant 2 is upper left where x is negative and y positive. Quadrant 3 is lower left where both are negative. Quadrant 4 is lower right where x is positive and y negative. The numbering goes counterclockwise starting at the upper right, a convention worth memorizing once and never re-deriving. Step 1 in plotting a point. Read the x-coordinate from the ordered pair and move horizontally from the origin right for positive, left for negative. The horizontal motion lands you on a vertical line through the chosen x-coordinate parallel to the y-axis. The first coordinate has been used and the second is still pending. Step 2. Read the y-coordinate from the ordered pair and move vertically from the position you reached in step 1 up for positive, down for negative. The vertical motion lands you on a horizontal line through the chosen y-coordinate parallel to the x-axis. The intersection of the vertical line from step 1 and the horizontal line from step 2 is the point you wanted to plot, and the point sits in whichever quadrant the sign combination dictates. Step 3. Optionally label the point with its ordered pair next to the dot, so the figure is easy to read by anyone else. Verify by reading the dot's coordinates from the grid and confirming they match the original ordered pair. The verification step takes about 3 seconds and catches the most common plotting error, which is swapping the x and y coordinates when reading or writing the ordered pair. Over the rest of the section, every figure you draw would use this same plot by coordinates procedure, and the procedure becomes automatic after a few dozen practice points. Here is the first worked example. Plot 4 points on the coordinate plane, 1 per quadrant. The points are 3, 2 in quadrant 1, negative 4, 1 in quadrant 2, negative 2, negative 3 in quadrant 3, and 5, negative 1 in quadrant 4. We will plot each one in turn using the two-step plotting procedure. Point 1. 3, 2. Read the x-coordinate 3 and move 3 units to the right from the origin. Then read the y-coordinate 2 and move 2 units up from that position. Land at the point 3 to the right and 2 up, which sits in quadrant 1 because both coordinates are positive. Point 2. Negative 4, 1. Read the x-coordinate negative 4 and move 4 units to the left from the origin. Then read the y-coordinate 1 and move 1 unit up. Land at the point 4 to the left and 1 up, which sits in quadrant 2 because x is negative and y is positive. Point 3. Negative 2, negative 3. Read the x-coordinate negative 2 and move 2 units to the left. Then read the y-coordinate negative 3 and move 3 units down. Land at the point 2 to the left and 3 down, which sits in quadrant 3 because both coordinates are negative. Point 4. 5, negative 1. Read the x-coordinate 5 and move 5 units to the right. Then read the y-coordinate negative 1 and move 1 unit down. Land at the point 5 to the right and 1 down, which sits in quadrant 4 because x is positive and y is negative. So the 4 points are plotted 1 per quadrant, illustrating the 4 sign combinations. The big lesson from this example is the systematic plot by coordinates procedure: x first, horizontal motion, y second, vertical motion. Verify the quadrant matches the sign combination. The procedure is mechanical and reliable, and after plotting 15 or 20 points, you will be able to plot any ordered pair in under 5 seconds without conscious thought. The quadrant identification is a useful sanity check on every plot because the quadrant must match the sign combination of the coordinates, and a mismatch flags an error in either the reading or the plotting step. Here is the second worked example. Identify the quadrant of each given point without plotting it explicitly, using only the signs of the coordinates. The points are 6, 4, negative 3, 7, negative 5, negative 2, 8, negative 6, and 0, 5. 5 points covering the 4 standard quadrants and 1 axis edge case. Point 1, 6, 4. Both coordinates are positive, so the point is in quadrant 1. The x positive, y positive sign pattern is the quadrant 1 signature. Point 2. Negative 3, 7. The x-coordinate is negative and the y-coordinate is positive, so the point is in quadrant 2. The x negative, y positive sign pattern is the quadrant 2 signature. Point 3. Negative 5, negative 2. Both coordinates are negative, so the point is in quadrant 3. The x negative, y negative sign pattern is the quadrant 3 signature. Point 4. 8, negative 6. The x-coordinate is positive and the y-coordinate is negative, so the point is in quadrant 4. The x positive, y negative sign pattern is the quadrant 4 signature. Point 5. 0, 5. The x-coordinate is exactly 0, so the point lies on the y-axis itself rather than in any quadrant. Points on either axis are not assigned to any quadrant, since they sit on the boundary between two quadrants. This is the axis edge case. Worth noting, any point with a 0 coordinate lies on an axis, not in a quadrant. So the 5 points distribute as 1 per quadrant for the first 4, with the fifth being an axis edge case. The big lesson from this example is the sign to quadrant mapping. Positive positive is 1, negative positive is 2, negative negative is 3, positive negative is 4, and any zero coordinate places the point on the corresponding axis. Memorize the sign mapping once and the quadrant identification of any point becomes a 1-second mental operation rather than a re-derivation. The axis edge case is also worth memorizing as its own special case because confusing axis points with quadrant points is a common subtle mistake on textbook problems and standardized tests. 3 mistakes that catch every algebra student during their first weeks of plotting work. Each one is fixable with a small explicit habit applied on every plot. First mistake: swapping the x-coordinate and the y-coordinate when reading or plotting an ordered pair. A student sees the pair 2, 3 and plots a point at 3 units right and 2 units up, treating the coordinates as y first then x. The convention is x first then y universally across mathematics, science, and engineering. The fix is to say the words x first then y out loud while reading any ordered pair until the convention becomes a permanent reflex. Second mistake: misidentifying the quadrant of a point because the sign to quadrant mapping is not yet memorized. A student looks at the point negative 3, 5 and says quadrant 3 because the first coordinate is negative but the y-coordinate is positive, so the point is actually in quadrant 2. The fix is to memorize the sign to quadrant mapping deliberately. X positive y positive is 1, x negative y positive is 2, x negative y negative is 3, x positive y negative is 4. The 4-line table fits on a single index card. Third mistake: miscounting tick marks on the axis, especially counting from 1 instead of from 0. A student plotting the point 5, 3 counts 5 tick marks starting from the first labeled tick on the axis, but the first labeled tick is 1 not 0, so the plot lands at 4 to the right of the origin instead of 5. The fix is to start every count from the origin labeled 0, not from the first labeled positive tick. The origin is the universal reference for every plot. The coordinate plane is the foundational data structure of all of analytic geometry, computer graphics, navigation, physics, and data visualization across the entire applied world. Anywhere two-dimensional spatial information needs to be encoded numerically, the coordinate plane is the encoding scheme. 4 broad sectors below. In maps and geographic information systems, every location on Earth is identified by latitude and longitude coordinates, which are essentially coordinates on a curved variant of the coordinate plane wrapped around a sphere. GPS receivers compute their position by solving systems of distance equations from satellites, then report the position as a latitude-longitude pair. Mapping software like Google Maps and OpenStreetMap stores every road, building, and point of interest as one or more coordinate plane locations. The coordinate plane skill underpins all of modern navigation. On every screen of every digital device, every pixel has an X-way coordinate within the screen's pixel grid, with the origin typically at the upper left corner. Game engines, web browsers, image editors, and video players all manipulate pixel coordinates constantly to draw graphics. The coordinate plane operations you learn today are exactly the operations these systems perform millions of times per second. In physics, the position and velocity of a moving object can be visualized as a point on a coordinate plane called the state space, where one axis represents position and the other velocity. The trajectory of the object over time traces out a curve on this state space, and the geometry of the curve reveals important properties about the motion that are hard to see from the equations alone. State space diagrams are foundational tools across mechanics, electrical engineering, control theory, and chemistry. In data analysis and statistics, every scatter plot, line graph bar chart, and time series visualization is a representation of data on a coordinate plane. The horizontal axis carries one variable, the vertical axis another, and individual data points or lines show the relationship between them. Spreadsheets, business dashboards, and scientific publications all rely on coordinate, plane visualizations to communicate data effectively. The plotting skill you build today is in continuous professional use across the entire information economy. 3 things to take with you from this lesson today. The coordinate plane is the foundational data structure of all of analytic geometry, computer graphics, navigation, and data visualization across the modern world. And the plotting and quadrant skills you build today scale directly into every later lesson on lines, slopes, distances, and graphical solutions to equations and systems of equations later in the algebra course. First, the coordinate plane consists of a horizontal x-axis that carries positive values to the right and negative values to the left, plus a vertical y-axis carrying positive values upward and negative downward, crossing at a single point called the origin. The 2 axes together create a flat, 2-dimensional grid that covers the entire plane, and every point in the plane has a unique location relative to the origin. Second, every point in the plane is named by an ordered pair x, y, with the x-coordinate listed first and the y-coordinate listed second, separated by a comma and enclosed in parentheses. The order of the 2 coordinates matters, x first then y, universally across mathematics, science, and engineering. To plot a point, read the x-coordinate and move horizontally from the origin, then read the y-coordinate and move vertically from that position. Verify the plot by reading the plotted dots coordinates back from the grid and comparing them to the original ordered pair. Third, the 2 axes divide the plane into 4 quadrants numbered I22EV counterclockwise starting from the upper right. Quadrant 1 has both coordinates positive, Quadrant 2 has x negative and y positive, Quadrant 3 has both negative, Quadrant 4 has x positive and y negative. Memorize the sign to quadrant mapping once, and the quadrant identification becomes a 1-second operation. Points on either axis itself are not in any quadrant. Coming up next, the lesson called Distance and Midpoint, where the algebra of squared differences and averages connects to the geometry of the plane to give the distance formula and the midpoint formula. Both formulas are foundational tools for the rest of Section 4 and for every later section that uses geometric reasoning, including conic sections in Section 15 and 3, dimensional generalizations in calculus.